Welcome to this explainer. Today we are diving into a literal heavyweight scientific matchup of cosmic proportions. On one side of the ring, we've got our current undisputed champion of cosmology, the standard model of the universe. And on the other side, a radically elegant new unifying framework that completely reimagines the cosmos. We're going to explore the fundamental nature of reality by unpacking the clash between the established Lambda CDM model and the scrappy new challenger. Dynamical Vacuum Field Theory, or DVFT for short. Let's get into it.
Here is our roadmap for today. We'll be covering the current cosmic recipe, a radical conceptual shift, why the standard model rules, where the challenger shines, and finally, the ultimate scientific test.
All right, Section 1, the current cosmic recipe.
Look at this breakdown of our universe. Only about 5% of it is ordinary baryons. That's the normal matter that makes up you, me, the room you're sitting in right now, the stars, the planets, all of it. Just 5%. Then we've got 27% cold dark matter and a massive 68% dark energy. The big takeaway here is that ordinary matter is dynamically subdominant. Basically, the stuff we can actually see and touch is just a tiny passenger in a universe driven by unseen forces. Most of reality is actually made up of these massive dark sectors that we don't fully understand, but we know they absolutely have to be there to make the math work.
Moving on to Section 2, a radical conceptual shift.
To really grasp why DVFT is so incredibly appealing, you kind of have to look at the reigning champion's messy closet. According to our sources, Lambda CDM treats spacetime geometry, dark matter, dark energy, inflation remnants, vacuum energy, and the cosmic web scaffolding as completely separate, disconnected ingredients. Sure, when you duct tape all these pieces together, the math works, but honestly, it feels incredibly clunky.
DVFT swoops in to solve that clunkiness by proposing a massive paradigm shift. Instead of being a bunch of separate sectors, it argues that all those disconnected dark ingredients are actually manifestations of one single dynamical vacuum field. It unifies them. It gives the universe a single cohesive vacuum structure, which, conceptually speaking, just feels so much cleaner.
Think about the contrast here. In the standard model, the universe is driven by an ocean of unseen particles, specifically cold dark matter particles. But DVFT, it completely throws that out the window. It replaces particle dark matter with primordial vacuum topology. So the structure actually comes from the vacuum itself, not from invisible particles floating around.
I want to pause here for a second and just let the philosophical weight of this quote from the source material sink in. Baryons are not the primary architects of cosmic structure. Under DVFT, the vacuum already carries the structure. The filaments exist, the voids are already there. Ordinary matter, the baryons, are literally just coming along for the ride. It's like, think of ordinary matter as mere condensation gathering on a pre-existing vacuum window pane. The matter isn't building the house, it's just settling into the architecture that the vacuum already built.
Which brings us to Section 3, why the standard model rules.
Now, you might be wondering, why haven't scientists jumped ship yet? Well, because Lambda CDM's math matches our telescopes perfectly. It quantitatively explains the cosmic microwave background acoustic peaks, baryon acoustic oscillations, lensing, and galaxy clusters. It provides this incredibly solid, globally self-consistent fit. So to dethrone the champion, DVFT can't just be conceptually pretty. It has to match or completely beat every single one of these empirical successes.
And history gives us a really good reason to be cautious. Over the decades, we've seen so many beautiful, unified field ideas and vacuum medium concepts pop up, but they ultimately failed because they just couldn't reproduce local tests of general relativity or accurately predict structure growth. The scientific community is naturally conservative because elegance is absolutely meaningless if it doesn't match the hard data.
All right, Section 4, where the challenger shines.
Let's take cosmic voids, for example. Under the standard Lambda CDM model, the massive empty spaces in our universe, these voids, are treated mostly statistically. They're basically just an absence of matter. But under DVFT, voids are given a direct physical meaning, a real physical ontology. Instead of just being empty space, they act as repulsive gravity hills that are actively pushing matter away. That is a fundamentally different and conceptually powerful way to look at the emptiness of space.
And voids aren't the only advantage. DVFT naturally explains large-scale flow geometry, like why galaxies seem to align with cosmic flows around the dipole repeller. Plus, here's a really exciting one. The James Webb Space Telescope recently shocked astronomers by finding galaxies that formed way too early. Well, DVFT's primordial vacuum wells naturally accelerate early structure formation, perfectly addressing this massive new mystery.
And it does all of this while bringing dark energy, dark matter, and inflation into one single vacuum origin.
Okay, let's break down this complex term, tachyonic Kibble-Zarek freezeout. Yeah, it's a mouthful, but this is the ultimate origin story. Long before stars or galaxies even existed, this primordial freezeout process created the underlying topological scaffolding of the universe. It's the blueprint that all ordinary matter would eventually follow and condense into.
Finally, Section 5, the ultimate scientific test.
What makes DVFT so sophisticated is its use of scale separation. In areas of high acceleration, like right here in our solar system, Einstein's general relativity works perfectly. But out in the vast cosmos, where acceleration is very low, the dynamics are dominated by that vacuum scaffolding. DVFT is attempting to simultaneously preserve general relativity locally while leaning on non-particle vacuum scaffolds on a massive cosmic scale.
Which leads us to the final, absolutely crucial question. Can DFT actually fit the data with fewer assumptions? Right now, DFT doesn't need more philosophy. It needs hard math. It must definitively prove that its vacuum topology predicts the flow of voids and early galaxies better than invisible dark matter. It's an incredible theoretical clash that could literally rewrite reality as we know it. So what do you think? Thanks for joining me on this explainer. Keep questioning and keep looking up.